Okay, good evening, all. We are now moving to the third day of AICT online FDP on emerging trends in electric vehicle. So now we have today we have with us Dr. Debanan Singh Dio from our team. So I welcome sir to the session. So for the official welcome address, I invite Freya to the
Okay, ma'am.
meet. Okay, thank you.
Good evening, everyone. It gives me great pleasure to extend a warm welcome to all of you to the AICTE Training and Learning sponsored online faculty development program on emerging trends in electric vehicle ecosystems, power electronics, AI, and sustainable mobility, organized by the Department of Electrical and Electronics Engineering, Christ College of Engineering, Irinalakuda. We are now on day 3 of this FTP, and it is truly encouraging to see your continued participation and enthusiasm. We are delighted to welcome Dr. Debanan Singhio, a distinguished researcher and industry expert with rich experience across academia and technology. Dr. Singhio is currently serving as a senior customer success engineer at MathWorks, where for the past 6 years, he has been enabling scientists and engineers to accelerate their projects in areas such as data science and model based design for electrification. His work involves supporting users, demonstrating end to end workflows, and bridging cutting edge computational tools with real world applications. Before joining MathWorks, Dr. Singdio was a DST Inspire faculty at Tezpur University, Assam, and a postdoctoral researcher at Aalborg University, Denmark, where he contributed to advanced research in energy systems and simulation. He earned his PhD in engineering from IIT Bombay, where he specialized his computational tools like MATLAB and ANSYS Fluent, following his master's in energy from IIT Bombay as well. His academic foundation and research expertise are complemented by his strong industry engagement, making him a true bridge between innovation and application. With over a decade of combined experience in research, teaching, and customer success engineering, Dr. Singdio continues to inspire young engineers and professionals in fields of energy, electrification, and computational modeling. So please join me in warmly welcoming Dr. Debanan Singdio.
Thank you for the very warm welcome, and a very good evening to all of you who have joined on this AICT Training and Learning FDP on emerging trends in electric vehicle ecosystems, power electronics, AI, and sustainable mobility. Okay. From my side, I will share my screen. And I hope it's visible to you also right now.
Yes, sir.
Okay, perfect. So the topic that I will take you today is exploring the trends in electric vehicles. So I will give you an idea about what is actually happening in the industries and how academicians such as us can be prepared for the change that is happening. So before beginning, I think I will just make one thing clear is that so electric vehicles is part of a bigger trend that we are going to see. So as I go along, I will touch multiple aspects of the themes of the FTP. So we will go a bit into electric vehicle, but we will also see how AI is also sort of impacting or improving the offerings when it comes to the whole automotive sector. Okay. So this is one photograph that I think the people who are typically born before 2000, they will be very easily able to rely, right? Uh, this is something that we used to see when we were young. So when it comes to automotives used to be just a vehicle that can take you from point A to point B. So initially, safety was not that big a concern. So if you look at the cars from that time, they would actually have no airbags, right? Even when it comes to the braking systems, we didn't have any anti-lock braking systems. And even in terms of entertainment, if you see, in many cases, we hardly had any entertainment, or in many cases, we had only radios. But things now have changed. Any modern car that you sort of are using nowadays, you'll see that uh, it is actually having so many different features. In fact, often when we go to buy any car, we actually think about the number of features we can have, and accordingly, automotive companies also position car in terms of different sort of feature brackets, right? There would be some base level car, then there would be some more features in a higher variant. So they would have multiple variants of the same car with different features. So what sort of features do you look for when you go to buy a car nowadays? Definitely, it has to have an engine, and there has to be a way the engine is able to transfer that power to the wheels. Is this something that I'm going to satisfied with? No. So we are also looking at something called drive quality. So whenever we are driving a car, we want to have a certain good experience driving it. So it should have a very good sort of a steering mechanism which is there. It shouldn't be hard. It should have a power steering. We should have very good sort of vehicle dynamics. So there has to be a ride control, some sort of a traction control, and to ensure that we are able to brake effectively, it has to has ABS. Now, if I give you this many features, how many of you are going to be happy buying a car like this? Okay, none, right? So in today's world, we are actually looking for more features than what you see here. Not just a car with an engine, not just about the drivability of the car, but we are looking at more options. So maybe I can give you something like this. So I can give you a car with some sort of an adaptive lighting system. For safety aspects, maybe I will give you something like crash avoidance technologies, airbags, detecting different sort of passengers. If you're going for long drives, preferably you might like adaptive cruise control. And to ensure that you don't bump into cars or nearby obstacles, I give you obstacle detection. Now, does this car become much more interesting for you? And would you like to go for a car like this? How many of you would like to go for a car like this? Nice. So at least some of us are interested in a car like this. And this is something that we see now. Okay. But in most cases, automotive companies, they are planning for the next generation of cars. So what they are nowadays also thinking of offering in cars is not just this, but other aspects, like we are looking at how you can have a very good infotainment system. You can directly connect your mobile to the car and play your favorite songs. Car should offer wireless connectivity. So we do not want to have any wires in the cabin. All we want to do is directly take our mobile and connect it seamlessly with the car. It should offer navigation options. So going from point A to point B, what is the best way to go to that place in the fastest way? This is a part of the navigation aspect. Uh, People are also looking at options like voice recognition, identifying whether the driver is drowsy. So features are, if you see, the more features there are, the more a car becomes sellable to the customer base, right? And you can sell it at a higher price also. So this is where the automobile technology today is going. Okay. So what is the key aspect of this whole transformation? If you look at the key aspect that ensures that we are able to offer more features, better features, one key aspect is the software aspect of it. So embedded software is actually key to automotive innovation. Okay, so if you look at this particular chart, this has been taken from something in 2008 to 2020. So where we have listed the important things that customers look at when they go to buy a particular car. So definitely one of the key things people look at is fuel efficiency, eco-friendly, so electric options. But there are also a lot of different things that come into the picture. Okay. So specifically in the competitive aspect, this is something that all of us actually demand. So most automotives try to meet these three. But the competitive aspect where we try to compare both of them typically comes from the aspect of comfort, convenience, the cost aspect, and the features that a particular automotive company is offering. Right. So with this, let's try to understand then where are we going? So how does the next generation of mobility actually look like? Okay. So what I will do, I will just talk about the trend that we see in the industry now. So in industry, what they are saying is that software has become very key aspect of the whole vehicle development process. So companies like Tata Motors, they are saying that cars of tomorrow are not just any equipment that we buy, they are like software on wheels. It has so much software that we can think of it like a software that is on wheels, right? Even not just Indian companies, like other companies like Volkswagen, who are sort of the European car manufacturers, they're also seeing how to increase the proportion of software in the vehicle that is developed in-house. So they want to not just develop the vehicle, they want to develop software also in-house. Renault is a French company, so they are also saying that the vehicle is no longer the central point of automotive value chain. So they go one step further and they are saying that the vehicle is actually no longer the central point of the automotive value chain. Primarily, software, electronics, onboard intelligence increasingly determine both the value and use of the vehicle for new mobility needs and services. Okay, so he actually says that what are the important selling points when it comes to the modern day mobility vehicles. So I will give you a comparison. Like this might not make a lot of sense to many of us, but we can relate it to use of one application that all of us are typically using. So as of now, if you see, all of us are users of mobile phone. So I'm not sure how many of you have had the mobile that you see on the left side, but I think most of us actually have the mobile on the right side. I hope this is a point of agreement. Why don't we prefer the mobile on the left side, and why do we prefer the mobile that you see on the right hand side? Why do you think it's more attractive to have the mobile? So what is the main thing that has given this change? So this shift from the mobile that you see in the left to the right is actually something that sort of was based upon customer requirements. Okay. So basically, if you look at this particular mobile, okay, the customer perceived value is actually not very high because we have certain expectations of a particular mobile. What expectations do we have? It is not just something that helps us communicate. What is the primary function of a mobile phone? I hope all of us are able to relate. Why do you actually buy a mobile phone for? Communicating, right? But if I give you a mobile phone like this, which is very good in communicating, maybe it has very good reception, I can give you 5G, 6G, would you actually go for it? I'm sure no is the unanimous answer. The reason is that our expectations have increased. Just from one device, mobile, we don't just want to use it as a communication device, we want to use it for multiple other applications also. Okay, this is one point. So what happened over a period of time was that they tried to update the mobile, newer versions came up, newer software came up. So once something new comes up, if you see, the interest increases. So once a mobile like this came, after that we had flip phones, so the interest increases for a period of time, and then again it goes down until something new comes up. So this is a mindset that all of us are sort of built, that whenever we buy something, we are always looking for something new in it. Okay, this is something that was made possible by the modern day mobile. So if you look at many of the modern day mobiles, the inherent platform doesn't change a lot. Does that year to year? Not a bit, not much. But what changes actually is the applications that are built there that allow us to do many new things. So we are able to align better with the customers, not by changing an entire mobile, but changing some of the applications. Okay. So this is the thing about this is that this is something that makes sense when you talk about cars also. So modern day cars, the main thing is that it should give us mobility point A to point B. That can be done by an IC engine, that can be done by an electric vehicle also. But what our modern day consumer is looking at is a lot of other things apart from the mobility aspect. So we already talked about smartphone integration. Infotainment is going to be a very important part of it. Okay. Infotainment means it has a combination of information relevant to my driving experience, like my speed, distance to my destination, the amount of charge left. But it also has capabilities of giving me entertainment, so I can control the cabin temperature, put on different sort of music, lighting, all those aspects. Okay, so we are looking at not just a mobility thing, but we are looking at something that can take us from that can offer us a number of features as well as personalization. Okay, so we do not take the car and change it very frequently. What is going to change is that the features that the car is going to offer, that we can inherently address just by doing some software changes. Okay, so this is where the whole automotive industry is going, and what they're calling this sort of new trend is software defined vehicles. Mainly there are three primary aspects of it. One is the AI and autonomy aspect. So cars are becoming more and more autonomous. We are trying to electrify it. So we are trying to see, we are trying to use technologies that reduce uh, uh, generation of carbon or CO2 or other global warming gases. And then we are looking at connected technology where cars are going to communicate also, and they might communicate among themselves, but they might also communicate with computational resources that might be situated somewhere else. So what are the things that make something like this transition possible? So behind the scene, what is happening? This is something that we are looking at from the megatrend perspective. But behind this, what are the technologies that are shaping this whole scenario is something that we are going to look at now. Okay. I hope this makes sense. Let me know if you have any questions so far. Okay.
Participants, if you have any question,
Yeah.
you can ask it now.
Please feel free to ask questions as we go along. Okay, so maybe I think this makes sense, then I'll go to the next part. So one very key aspect of this entire transition is the changing architectures of modern day vehicles. So if you look at the vehicles that were there conventional 2010 and all, okay, we have a number of features on the vehicle, that is great. But if you look at the architecture, basically what is happening is that there used to be sort of a central architecture, and there used to be distributed control. So centralized architecture means, distributed architecture means that basically there are so many different things are being controlled, but the code that you generate that does all of these controls, that is coming from one central place. So if you look here, there would be some sort of a central computing unit, okay, and that effectively is where or you can think of like it like a control chip, the ECU, the electronic control unit of the car, and that is where the uh, computing programs that would control different aspects of the car would be residing, okay. But what happened over a period of time, if you see, as we are offering more and more features, uh, the car is definitely going to have more and more lines of code. Okay, so who is going to do the computing for the car? So we need to be adding computing power. Okay, so we need to have better computing power to address all of these things. Okay. But would computing power be just enough? That is not just enough. We need actually new architectures to consolidate and centralize the computing power into some small number of vehicles and zone controllers. So we are actually moving away from distributed architectures where we had different sort of control units. So you can see here, this one has a lot of different control units. We are just moving away from there, okay. So you can have something like zone based architectures, what we see here, zone based architectures. But in the future, if you see, the entire architecture is also sort of shifting, okay. So here we might have some computing power on the car, but we might have also very good cloud based connectivity with which we can have some sort of computing on the cloud as well, okay. So high performance computing platform and new architectures are not just enough to realize the promise of perpetually upgradable software defined vehicle. So what automotive industries are looking at is a new architecture. So this new architecture is not based on signals. So in a modern the automotive, most of the control aspect is based upon signal, which are typically time driven. Okay. But in future, what we are looking at is a service-based architecture, in which case the architecture itself will change. It will be a event-based architecture. Okay. So this is one key thing which is there. I will not delve a lot into the architecture aspect of electric vehicles. Uh, uh, just one moment. Yeah. What I will give you a place where you can get started if you are interested in the architecture aspect of an electric vehicle. Okay. So if you're interested in this architecture of modern day vehicles, a good place to get started is to understand what is actually a systems architecture. What are basically requirements? Okay. So what are requirements? Requirements are specifically whatever aspects or features or capabilities the car is going to provide to me. And often what is done is that based on this requirement, first thing that we do is create a system diagram where all these requirements are connected. Okay. After doing this, then we go back and actually do the component level modeling. If this is very new to you, one aspect you can relate it to is to look at the tools that are used. Okay. So all of you are familiar with Simulink. Okay, Simulink is basically related to component level modeling. So we are actually building model for each and every component. Okay. For this system, what we have is something known as system composer. So in case of a system composer, we build a system level diagram of what are the different aspects of the car and what features that particular system does. And we look at the different quantities that are connected to that particular system, and then we connect it with the requirements that the car has to fulfill. Okay. So if you're interested in system aspect, we have a very nice introductory course that takes you and gives you an idea of how to create systems and their requirements. So you can take a look at this one. There's a system composer on-ramp content. In 1 hour, you should be able to create systems, system architectures. Okay. So this is one aspect, that how you sort of define the systems of the cars where we are talking about software defined vehicles. Okay. The other aspect which is also very important is that we have to understand data-driven workflow. So this is a very key trend that we see in the industry. So we are talking about in modern day cars, we generate huge amounts of data, right? There are sensors for so many different components and they generate a lot of data. And if we are able to leverage this data, we will be able to build very good sort of features for the car, and we will be able to personalize the car for each and every person who drives it. Okay. So personalization is something that we all like. Data-driven workflows are going to help us create that sort of features. So over time, if you look at the transition, so this is taken from a Gartner report from 2019 to 2022, you can actually see the average number of AI or machine learning projects deployed. Deployed means that it is being used in modern day cars. Okay. So it has actually from 2019 to 2022, it has gone about 9 times. So close to 9 times shift has happened. So organizations actually see, so organizations are able to foresee that in future also there is going to be substantial acceleration in their adoption of AI powered applications in cars. So I think this trend is clear that we are going to see more and more use of AI in different sort of applications for cars. So how do we go about building something like this? So I will take you through an example that shows how you can build an AI related feature for any given application. Okay. So we will take an application of a battery. So AI in itself is not a thing that is there in silo. It is often a part of a bigger system. Okay. AI is going to be part of certain systems. It is not something that is there on its own. So one example that we can sort of take a look at is that how we can use or integrate AI in a battery management system. So battery management systems are systems which are coupled with batteries, and they ensure that the battery sort of is able to work in the most safest option, and it gives us a good range for the vehicle, and it ensures that the vehicle is sort of able to deliver this power without any major safety constraint. So there are two aspects of this. One is actually the model of the battery. So there is going to be a battery plant model. The plant model is the model of the entire battery pack along with the power electronics. And this is going to be connected to the load. There can be two types of load. One type of load would be the motor where we are delivering power, but the other type could be when we are charging the battery pack. So then also we might have to connect it to some charging infrastructure, and how it sort of charges or discharges of batteries again going to be sort of decided by the battery management system. So it is the supervisory control logic aspect of the battery pack. So we have the battery pack and then we have the supervisory logical aspect. So can you guess here that where would you actually use AI in a system like this? In a system like this, where would you actually use AI? Can you take a guess for that?
Real-time monitoring and communication.
That's a very good find. So, and why would be my next question. Why would you do that for real-time communicating? So communicating is just sending data, right? Or would you actually need AI for that? Okay, so let me know if you are trying to answer. But the thing is that just for monitoring, I might not need, even for real-time monitoring. Okay, I can use, yeah, real-time monitoring we can use, but specifically I'm asking like which part of the system would you use? So we have so many different components here. Where would you actually use that?
In the BMS.
That's correct. So you'd actually use it in the battery management system. So that's very correct. Uh, in battery management system, there are so many different ways in which you can actually use AI. So one aspect is using AI as a virtual sensor model. Okay. So I will show one example of state of charge estimation where AI plays the role of a virtual sensor. So we are actually doing some sort of state monitoring. So why do we do state of charge measurement using AI? So one key thing is that we cannot actually directly look inside a battery and gauge how much amount of charge is there. The only thing that we can do is we can actually measure the current that the battery delivers. So either we can measure how much charge the battery delivers during discharging, or we can also measure how much current I'm storing in the battery during charging. But I cannot directly look inside a battery. So it is not like a bucket where I'm filling water and I can see the level of water that is rising, right? So we cannot directly look inside the battery and see how much charge is there. So it is not directly measurable. The other thing is that even if you try to indirectly measure, let's say I try to measure the voltage or something like that, there can be some sort of a error when it comes to the measurement of those sensors. So because of these two factors, what people are looking at AI related applications when it comes to state of charge monitoring. So virtual sensor is nothing but a physical sensor where we are using some data to estimate a particular quantity of interest. So it is we are talking about state of charge, but we can have different sort of physical sensors which are there. Okay. So here I have an example of some sort of physical. If you take any physical sensor, so there are certain inherent issues with that also. Okay. So problems could be something like the expense, or it could have a certain sort of speed to that, or it could be noisy. There could be some sort of reliability problem. In many cases, you cannot have a feature like that. It might not be something that is feasible. Okay. So there are so many different factors because of which we might not actually go with a physical sensor. So this is something that we might need to keep in mind when it comes to virtual sensors. Okay. So what do we do then? Then this makes the case for actual virtual sensor modeling. So when it comes to virtual sensor modeling, we can refer to this sort of I would say, chart. So data-driven model typically fall into the left-hand side. So right-hand side, if you see, we talk about physical first principles models. So where we know the equation, where we might know the math, we might have the domain knowledge. There we actually go with first principles modeling. But when we talk about data-driven or AI-based model, people also look at this like sometimes like black boxes. Okay, so it has its own reputation. But the interesting thing is that it's not like it has to be either first principles or data-driven model. They can actually also coexist. So you can have models where there is some sort of mathematics involved, and then you have AI. So that should also be possible to have. So broadly, when it comes to AI, there are so many ways we can go about it. Okay. So this reflects the AI megatrend. So AI is the broader spectrum where it includes technologies like machine learning, and then it includes something called deep learning also. Okay. Just a quick check. Are you able to hear me clearly, or is there some noise also in the background?
No, sir, you can hear.
It's clear, sir.
You are audible.
Thank you very much for the feedback. So So this is sort of the complete sort of a map when it comes to the field of AI. So AI is any technique that enables machine to mimic human intelligence. We can do it by training it on some data where we tell the machine that these are some of the features of the data, or there are methods where they directly learn from the data. We do not need to tell what is there in the particular data. The only difference between both of these two methods is that when it comes to machine learning, we have to explicitly program that. Okay. Sorry, we do not need to explicitly program that, but we need to sometimes give them some good features. But if it comes to deep learning, we might have a lot of different layers, but we do not need to explicitly give it any particular feature. Then there are some advanced methods also, like reinforcement learning, where also the it will automatically interact and learn. So that is also there. So today, what we are going to see is that how you can build something like this. So here, what you see here, there is an SOC estimation algorithm learning. It's an AI algorithm. And what it is trying to do, it is actually running on a given hardware. And then it is trying to predict the SOC of a battery. So we have the measured data, which is there. And we are having the SOC estimation algorithm running, and we are trying to compare both of them and trying to see how much they match. This is something that we want to sort of build at our end. Okay, end to end, like from the beginning to the end, this is something that we want to build, deploy, and test. So what would be the first step? First step is definitely we might have to sort of I think I'll just come here. Okay. So first step is to just understand what is the current state. So SOC estimation, although we are talking about AI, there are other methods also to measure it. One is the common method known as extended Kalman filter. Okay. So basically, compared to the extended Kalman filter, where we actually have a mathematical model estimating the battery state. So Kalman filter is able to estimate certain states. In case of this AI model, we need data to train the algorithm. So what data do I have at my end? I have some data from experiments. We have measured the voltage, current, and temperature of a battery during charging and discharging. So we want to train an AI model, and the AI model should be able to predict and give me the battery state of charge. Okay. So as I talked about, Kalman filters, people have been already been using before people started going for AI related methods. So some of the typical things that distinguishes both of them is that there is the feature, if you look at the data, there is nonlinearity. So both sort of AI typically handles it better, but in case of Kalman filter, we need some additional EKF, UKF sort of a thing. Data, in terms of data requirement, if you look at the present method of modeling using Kalman filter, you need very accurate model. Okay, so accurate model is needed, but in case of AI, we do not worry about that. We need a lot of data. And in terms of use, Kalman filters have long been used for state of charge estimation, but AI, it is emerging, and rapidly it is sort of being adopted by the automotive companies. But the good thing about the AI model is that once if you are able to train it, it can adapt actually very well to different battery chemistries. But in case of the Kalman filter approach, you might have to go back and again sort of parameterize the model which is there. Okay. So this is one of the advantages that AI actually offers. The other thing is that in case of a very good data set, if you have at your hand, you can actually improve the accuracy. Okay. So with what happens is that this is sort of like a static method in some ways, but in case of AI, when you have more and more data available, your prediction capability becomes better. Okay, so this is one advantage that AI actually offers. And finally, it is not like that you have to choose either between AI and Kalman filter. You can actually have a combination of both approaches. So this is also something that is possible. So battery state of charge estimation, this is the thing that we are going to look at. We have three things: voltage, current, temperature, and then we are going to train an AI model to do the state of charge prediction for the battery. So first step first, the workflow that we will use will have certain parts. So first step is actually data preparation. We need access to the data. Only when we have access to the data can we start for the next step. So depending on the data, in our case, the data is simple, but if you have very specific data set, you might need some sort of a domain specific pre and post processing. Then we look at building the AI model. MATLAB has a low code approach where using apps, we can actually create the AI model. In case we have a very good model at our side, let's say some sort of researcher or some sort of a domain expert has already built a model in other open source frameworks like PyTorch, TensorFlow, we can leverage these models. We can import it into the MATLAB framework and create our AI model. Third part, which is also very interesting, is simulation in testing. So how to take the model built, the AI model, and use it for simulation and testing is something that we are going to look at. Okay. And then often, whatever models you are building, it might not be enough to run on a hardware. So there are methods to do some sort of a compression to reduce the overall model size, and this actually accelerates the pace at which it can do the inferencing. Okay, so these are all the different steps. Once this is done, then we actually deploy it to different sort of targets. So one very important aspect of the whole choosing between AI or a conventional approach is also accuracy. So AI models typically run fast if you are able to sort of optimize the size of the model, if you are able to reduce it, and so what you can do is that you can have faster running model, but then we also should see what sort of accuracy we are getting. So there is sort of a scenario where we need to optimize between speed or accuracy. So the data that we have at our site, I have given the link for that. So we have a data set from one of the universities, McMaster universities. Okay. So just these data sets are not enough. What we do is that we are going to employ some sort of machine learning. So we create two more. So we are doing a bit of data processing to compute the moving average for voltage and moving average for current. Okay. So then our data preparation involves this transformation of the initial data, and then once we have that, this will be the entire data set that we can use. Okay. Then we decide what are the predictors. So we can choose the predictors from the data that we have at our site, and the response variable here is the state of charge. Okay. So there are different methods, as I mentioned, that can be used from the AI perspective. We can actually go with classical machine learning or deep learning ones. So based on this, there are different sort of methods we can employ. Okay, so I will not go into the detail of this right away. There are different sort of methods which are there, and then if needed, we can also go for a hybrid approach where we can have both AI and Kalman filter. Okay. So let's look at the first option where we can train a machine learning algorithm in MATLAB. Okay. Then the second thing we are going to look at is train a deep learning algorithm, and then finally we can show you how to actually import different sort of TensorFlow or PyTorch models also. Okay. So training in the MATLAB's machine learning framework, all we need to do is here, if you see, this is sort of the interface. So if you just run this, we have the data. It will actually load the data at our end. Okay. So we can see the number of samples here, and then we can have a brief overview of how the data looks like. Okay. This is the overview of the data, the app, the regression learning app. So there is a very nice app which is there in the app portion of MATLAB. If you just go there in the machine learning and deep learning part, so it's known as regression learner. So in this app, we can actually import the data set that we have, identify that the correct response, the response variables are chosen. Okay, so SOC we have taken out because SOC is the predictor. And then directly I can choose the different algorithms for machine learning. So all quick to train means at one given instance, all the different sort of machine learning models available to me, which are very quickly trained, I can train that. So at one given point, if you look at the left part of my screen, I am training multiple machine learning models at once. And then I can compare the accuracy of all of these data sets. Okay. Then I can actually go for the different sort of comparison with the test data set. Okay, so I have some test data sets, then I can do the testing part also here. So I will run certain tests, and then I will be able to compare the results of all of this. Okay, so here if you see, I have here if you see the different models which are there, the maximum accuracy is something that I can look at from this particular variable RMSC, and then whichever one gives me the maximum accuracy, I can export that model back to the MATLAB environment. So just by using an app, so this is the variable, the trained model. So this is a tree model that we sort of took because the root mean square error for this one was the lowest. So once we are happy with that, we can take the trained model and then we can take it back to the MATLAB environment. So it will export the model to the workflow, to the workspace, and in the MATLAB workspace, I can find the trained model. Okay. So very easy steps, very intuitive and interactive also. We just need to go through that. So once we have trained a particular model, then we can train and test it. Then we can take this model and connect it to the system level model for the battery management system. Okay. So this is just a comparison with the data that we had from the lab. The blue one is the SOC from lab, and the red one is the data estimated with the machine learning model. Okay. What are some commonalities that we find here? The commonality is that it is sort of able to capture the trend which is there, the broad trend which is there. So probably if I take a moving average of the estimated estimation from the ML, I might be able to sort of meet the data from the lab or correspond well with the data from the lab. But here if you look, typically what I observe is that this is charging and discharging data. So this is discharge and this is charge. So what I have observed is that charging part it is able to sort of measure quite accurately. But if you look at the discharging aspect, there is a lot of fluctuations which we see here, right? So this is a common observation that with a machine learning model, we see fluctuations specifically for the discharging aspect. Okay. For a EV application, which aspect is going to be very important for us? Charging is definitely important, but I am very much interested in the discharging part, right? Because this will actually determine the range of the vehicle. So if you have a machine learning model, like the one that I've trained, do you think something like this is going to be useful for being integrated to the battery management system? Would I take something like this and integrate with the battery management system? So this is the question. So let me know who would be interested in integrating with this with the battery management system, if anyone thinks so. Okay. No, right? Because it is not able to sort of accurately capture the discharging curve, which is very important for the range prediction. So this is not helping us a lot. So maybe we can try with some other methods. That is totally fine. So what are the things we can do here? We can go with maybe a better machine learning model, or we can get better data or better features with the data. These are some options available to us. Okay. Now let's see how a deep learning model might work. Okay, so Same data, nothing changes, but we are going to train in deep learning framework in MATLAB. Okay. So this is the example where we are going to train a deep learning model, a feed-forward network. Beginning steps are same. We access the data, load the training data. Okay. Then we look at the data. The very same data is there. Okay. Now what we are going to do, we are going to train a feed-forward neural network model. For doing that, we will use a different app. There is an app for deep network training, deep network creation. It's known as the Deep Network Designer app. This is something that we are going to pick from the tool stream. So again, we go back to the very top, or we can run the section also. It should open up the Deep Network Designer app for me. So Deep Network Designer app is where we interactively build networks. So if you look at the left part of the screen, I have a number of layers which are there. So basically this allows me to bring in any particular network, or I can create my network from scratch. So what we're doing here, we are taking layer by layer from the left pane and we are creating a network from scratch. So first layer here, if you see, it's the feature input layer because we have certain features with the data. And the final fully connected layer is where based upon how the features, how the network is trained, final fully connected layer is where I will get some sort of an output that then I can use for my application. So how do I create this? I can actually go and create it step by step. Okay. So let's say I need this sort of layers. I can actually go look at the activation layer, get the particular layer that I need. Okay. Then I have one more fully connected layer. So however, the network architectures I have, if I know it well, I can go there and design that particular network. So output, I am basically trying to predict state of charge. So it will be 1. And feature input, if you see, we have a number of features. So that also we need to sort of identify the feature and make the required changes. So in the end, so if you see here, I will just go back slightly. If you go to this part, we can actually look for errors. So there is something that looks at the entire network and it tells me that whether the network I have created is correct. How many learnable quantities are there? So if you see here, there are 897 learnables and only 4 layers which are there. Okay. There are no errors, so I can take this particular layer and then I can export it to my workspace to train. Okay, so once it is there in the workspace, we can actually start training. So we are generating a script also here. Sometimes it's not enough just to create a network. We want to ensure that how I created the network, that is also saved. So those aspects from the app, we can get a script. So next time I do not need to create something from scratch. If I just run this, it will create a network for me. Okay. So once the network is there, then we can start training it. So this is the training aspect. If you look here, so should train model, it's true. We are using a solver known as Adam, giving some initial learning rate, some sort of size, some sort of maximum epoch. And then we give it some options for training. Okay, so based on the data, now it will train my deep learning model. So it's good that I have the entire thing saved. So I can actually show you how the training goes. Otherwise, in a CPU, it is sort of going to take some amount of time to train it. Okay. So after training, we can see the loss has actually decreased. Okay, and the accuracy should actually go up. But here, if you see, I don't think the accuracy has actually gone up. Okay. So in those cases, we can just what we can do is that we can make some changes, and we can sort of try to see how the accuracy improves. And then in the end, we can actually test it and see what sort of result we are getting. Okay. So here also, if you take a look at the results, what we have here is it sort of is able to align with the discharge curve, but here also we see there are a lot of fluctuations when it comes to the deep learning model, right? Charging, it is very accurately able to predict, but discharging we see this sort of a fluctuation. Okay. So we see machine learning and deep learning also sort of finding it challenging to predict the discharge, right? Okay, so I'm not sure if this is the same one. Okay. So let's do one thing. Let's try something different. So we train it as an LSTM network. There is one more different type of network which is known as long short-term memory, where there are certain memory cells which are there, which is able to remember some data. Okay. So now the network architecture has changed compared to the previous one, if you see. Okay. Compared to the previous one, we have some LSTM layers which are there, which is sort of able to remember the past step data. So there is some memory element which is there. Now let's see whether we are able to have a better network. Okay. So nothing changes here. Only the network architecture we are changing. Okay. Then we are sort of going and we are going to train this particular network. We have just created this particular network. Now we are going to train this network with some data. Again, we are able to sort of track the training. If we are happy with it, we can go forward and use the network. And if not, we can go back and change training parameters and try to go with a different options. We might have some sort of better network accuracy. So now let's see if we are able to test this network. Does this give me better sort of accuracy when it comes to the entire thing? Okay. So again, compare with test data, but again, we get something like this. So now if you see with an LSTM, although it is able to remember some sort of a past information, you still see that there is a lot of fluctuations when it comes to the discharging curve, but not when it comes to the charging curve. Now, if somebody is from this background, let me know why do you think they are having problem sort of following the discharging curve, and why they are able to follow the charging part so well. Okay, let me know. This question is for you. Why do you think it is struggling with this leg, but it is not struggling with this leg? As humans, we are able to tell very clearly, right, that what is the trend of the SOC data, but for the program, learning this part is actually very challenging. Why is the challenge is something that I pose as a question. Okay. Is this done? Okay. Now let me try what I can also do is that let's see if something from any other framework might have any better accuracy. So if I want to go and try that out, that is also possible from MATLAB. What I can do, I can actually import PyTorch models or TensorFlow models, and then I can use the same data and compare how this compare. So we can use the import tab for that. So there is a very nice import tab for that. I will just show you once again. So whenever you open this sort of deep network designer, we have these tabs which are there. Okay. There is a PyTorch tab. There is a TensorFlow tab. So if we have models of PyTorch or TensorFlow, we can import them also directly. So once I import that, we should be able to see it here visualized. So .pt is the extension for the PyTorch model. We are importing it and we are sort of visualizing everything. One thing that we have to do here is that it is not able to understand the input size here. So we have to tell it explicitly that what is the input size of the model. Okay. Whenever you are importing any model, just to showcase it again, whenever you press the import tab, it will ask you that what is the import specification. Okay. This is one aspect that we need to take care. If we do that, then it will be taking the PyTorch model, converting it into a MATLAB network, and then we can see that particular networking designer. Then it is always good to analyze them just to check if there are any warnings. So we can see how many learnables are there. Then we can take the same network to the workspace and train it like the way we have learned how to train that particular network. Okay. And if needed, we can also generate some code out of that, so that next time I don't have to do the same steps. Okay, so once I have the network imported, the remaining steps are going to be the same. Okay, we can sort of, okay, so this is we can import it by program also. It's always not necessary to use deep network design, that is fine. But once we have a network like this, what we can do, we can also test out this particular network and see how they perform. Okay, so these are just networks that are already there, trained different framework. We can try to see how the performance is. Okay. Again, we see the performance doesn't change much, right? We see this sort of a performance here. Okay. But this is possible now. So we can train networks from other frameworks and we can also train them. Okay. So once you've trained the model, then you can go to the next step where you integrate it with a system level simulation and test them out. Okay. So this is where MATLAB is also very strong now. So we have Simulink, which is the main platform for modeling different engineering systems. So in Simulink, we have libraries that allow you to bring the trained network. So any AI network, maybe you are training it from machine learning framework, you can use these sort of blocks to bring them to MATLAB environment. So if it is a regression tree you have modeled in machine learning, if you have that sort of a model, you can use the regression tree predict block. If you have an SVM, then you use the regression SVM predict block. So for different sort of frameworks, statistics and machine learning, we have blocks that allow you to bring the trained model to the Simulink platform. Now, what about deep learning? Similar thing for deep learning, there are blocks that allow you to bring the trained model to the deep learning environment. Okay. And similarly, if you're working on system identification, if you're working with audio or computer vision toolbox, there would be certain libraries that allow you to work with these AI models. Okay. So some AI models you might have trained for, let's say, some audio data. Then you need audio toolbox and the libraries for that. If you're working with object detector, you need the computer vision toolbox. So all these libraries allow you to build the entire engineering model and integrate AI in that. So now let's look at how you can integrate the model into Simulink. Okay. So now first thing we need is the trained data. Okay. Trained model. Some test data, the trained model. So model inputs we are taking, and then we are going to integrate that model in Simulink. Okay. So here we are using something called the variant subsystem. There are all different sort of models here. So there is Kalman filter, there is a feed forward network, LSTM network. So just by one block using variant subsystem, I can have different sort of AI models which I can bring here. Okay. So here I can also select which model I'm working with, and accordingly that particular model will open up in the Simulink environment. And then I can run simulation and look at the output. So here we are just running the simulation in Simulink, and then we are comparing the output that we are getting from Simulink. So this is a Simulink block. We are able to see the Simulink output here. And then we can compare the different models, and we can see what is the accuracy level of all of these different models. So integration is actually very easy. You have dedicated blocks that allow you to integrate these algorithms into the Simulink environment. After this, we can actually do system level simulation. Okay. In case of system level simulation, we will have some data, and then we are trying to predict that using the models that we have created. So you can see the neural network model. We can see the red one, which is the EKF model. The green one is actually the data that we have, the true data. We have the neural network, and if you look at the red one, this is the EKF one. Okay. So we can have a system level comparison of all the models together. Okay. We are giving it a certain test sequence, and then we are taking the results from all the variants, all the different models that I have trained, and we are able to compare them together and see the effectivity of all of these models. Okay. So once this is done, what is going to be the next step? The next step would be to see how I can take them to the hardware. Okay. So even before doing everything on hardware, what we can do is a processor in the loop testing. Okay. So basically, in processor of the loop testing, I can generate code from the BMS algorithm. So I have integrated the state of charge algorithm specifically with the BMS. That is going to run on some hardware, right? So BMS will run on the BMS ECU. So that is the hardware which is there. So I have to generate this into code inherent for the specific hardware target. So here we have an NXP board. We are generating code from the algorithm. On the other side, what we are doing, we are taking the deployed code and it communicates with the simulated plant. The simulated plant here in this case is running on the processor of the computer that you have. Okay. So both of them are sort of communicating, and we are able to test in a processor in the loop testing that how the BMS is sort of working. Okay. So this is just an example taken from the hardware part. So we can go to settings, identify that we are using the correct hardware target. So here we can see we have the NXP board here with the communication happening through the serial port COM port 7. And then we can run it in a software in loop, processor in loop tab. So then SOC estimation is actually happening now on the hardware, the NXP board. And now we are able to see how both of them match. So the measured SOC, it is running on the processor, and we are comparing how the both of them sort of compare, and we can see that data right here. Okay. So this sort of tests we can do after we have created the model and integrated it. Okay, so this is the whole report from the testing, the estimation part, and we can actually look at the code generation aspect here also. So directly we can generate the code of the AI model for any given hardware target. So that is the best part about it. You need not worry. You take the AI algorithm, integrate it with the BMS, the BMS model, and then you can directly generate the code for any given hardware target. And then you can do this sort of testing. So who are using this? So I have taken one example just to showcase that which industries are using. So there is a company called Goshen. Okay. So they actually have created a virtual sensor with a neural network, SOC virtual sensor, state of charge. And if you look at this, they have taken everything and they have done a hardware in loop testing also. So some of their experience is that the execution of this sort of models is very fast. It is about 51 microsecond per call. Okay, so it executes actually very fast. And if you look at the whole memory size also, it is actually quite small. And overall, if you look at the numerical equivalence for the error also, the error that you see between what you have as measurable and what you have here is actually very less. Sorry, is there a question? Okay, yeah. So what you have here is that you have the whole SOC virtual sensor generated with a neural network and deployed. It has a very less memory footprint and it actually runs very fast because of that. And overall error they found was actually also very less. Okay. So not just this, this is sort of something that we are seeing the automotive companies like Mercedes-Benz also using. So they actually created something known as a virtual pressure sensor using AI, and they were able to train a Python model. You can see here they actually took a machine learning model from Python. Then they trained it in the MATLAB environment, integrated it with the engineering model, and then they generated custom code. So they use certain libraries to generate the custom code for the target hardware. Okay. So this is where you see the benefit of using MATLAB and Simulink. This aspect of taking AI and integrating it with an engineering system for a particular task. Okay. So not just automotive companies, even somebody like Coca-Cola, they have used this workflow for a beverage dispenser machine. So they have a machine which dispenses some sort of drinks, and they were able to create a virtual pressure sensor with machine learning and able to integrate and test with the particular hardware. Okay. So we looked at two different aspects till now: software architecture, which was a mega trend, and integrating AI with engineering systems, which is the other mega trend. The third important trend that we see here is cloud workflows. I'm not going into a lot of detail here, but you can already understand that the amount of data that is being generated, we also want to get very good sort of insights from the data. So there is a lot of interest around shifting some amount of the computation to the cloud. Okay. And what will happen is that based on the data, newer features or better algorithms will be created, which again will be deployed to the vehicle that we have. So a lot of effort and funding is going to shift some of the workflow to the cloud. So specifically for the vehicle development, automotive companies are looking at DevOps related solutions. Okay. So you can see that in a period of time, what they are also looking at is revenue. So even the revenue that they're getting from this new service, okay, from the cloud is actually increasing. So on our own point, we have some experience about cloud-based computation, specifically from ride-hailing apps. So all of us use Uber, Ola, where if you see what happens is that they compute the price on the cloud. Okay. Even automotive companies are looking at similar sort of solutions. They're looking at revenue from the cloud. Could be a better AI model, could be some sort of newer feature which we can have. So remote services, software upgrades, these are things that are going to be something that automotive companies are investing a lot of time and effort in. Okay, why? Because a vehicle you can sell only once, but after selling the vehicle, you can have additional revenue from the same vehicle just by looking at these things. The last thing that I'll just talk about is virtual validation. So often with so many features, it is very important that we just don't build something, but we validate that it is working as per the requirement that we have. So companies are investing in virtual validation. So they are building prototypes, and in a virtual environment, they are validating that how it is actually working out. Okay. So MathWorks, we are also in this particular space. We have a lot of examples that can help you get started in this particular space. One, so you can actually build models from scratch, component-wise, the entire system, and then we have, you can actually test them out in virtual environment. So we have something known as Roadrunner, where you can create virtual roads and test out how a vehicle actually works. And there are multiple different methods to go there. But one very quick thing that I will show you, which can get you started very fast and could be effective for academicians like yours, is a virtual vehicle composer app. Okay. What happens is that, like the app workflows we have seen before, you do not need to do a lot of steps. You just need to click that particular app. It's a very interactive thing. What you have to do effectively is start a new session, identify what vehicle you are building. Is it a conventional vehicle? Is it a four-wheeler? Is it a two-wheeler? Then you have to identify the powertrain. Is it an electric vehicle? Then how many motors does it have? Probably if it is hybrid vehicle, then what is the architecture? So you have to select the appropriate architecture for your vehicle. Okay, we go with one of them. You can select model templates also. what libraries it used to create those that particular virtual model. We can go with Simulink based components, or we can have Simscape components also. Okay. Then we decide the vehicle dynamics. Is it going to be a longitudinal one? It will, or something else. Once we decide that, it will create for me a vehicle parameterization chart where I can decide what is the vehicle's weight, what type of car it is, what sort of engine it has, whether it is a SI engine or whether it is a, if we go with electric motors, whether it's an electrified engine. So a lot of parameters are there. All we need to do is customize that. So for a hybrid one, we need to identify the motors. So we can take the motor torque, speed characteristics and directly feed them here. We can look at the corresponding efficiency map for the different parameters. And we can resize them also. So this is a very good tool where you can start with one motor rating, and then you can test whether for the performance that you are looking for, that motor rating is effective or not. So once you have parameterized, you can look at the torque speed characteristics. Then you can decide on the scenario. You can have different sort of drive cycles to test your vehicle. Okay, so there are different sort of drive cycles which are there, and you can have 3D scenes also. Sorry, I went a bit fast. You can have 3D scenes also. So in a virtual world, you can actually see how that particular virtual vehicle is working. And then we allow it to build the virtual vehicle. From our side, we do not need to do anything with the model. It will build the entire model end to end. Now, if we want, we can go and customize it. Okay. After building this, we can go and customize it also. And then we can do a virtual testing, different maneuvers or different sort of conditions we can place, and we can actually find out how that vehicle is actually performing. In Data Inspector, I can go and look at the different sort of vehicle characteristics, battery current, battery voltage, battery SOC, all of those parameters I can monitor here. It's a very unique, flexible solution. We can very easily customize at our end and then try to see whether it meets our requirement or not. And a lot of companies are actually trying to use this now to front end their development process. So it saves them a lot of time and effort in testing part. So companies like Ford, they actually automatically build, so they automate the whole model assembly. So whatever we did now, companies like Ford actually do. So they have some tool chains, they have certain models which are there. So all they do is that they sort of combine those models and run simulations. Okay. So here you can see that they have a system, it's called FASST, and it allows them to actually do virtual simulations. Okay. So they can go from start to the entire model building process very fast and are able to test it very fast as well. Okay. So lastly, I will not go into this aspect. Where do you get started? Okay, there are two things. Maybe I'll just talk about that. What sort of roles are being looked at in the industry? So when it comes to EV leaders, they are looking at these sort of things to focus on, like optimizing systems, new competition, developing new competencies, benchmark, setting different benchmark, managing complexity. Then there are roles called system architect. So there are a lot of roles coming, not just in automotive, but in aerospace as well, where they design the system architecture. So people work on the architecture aspect of things. Then there are roles in the area of software creation, where one can be a developer, one could be a person who is integrating AI or integrating software into the CI/CD pipeline. Okay. So, and then there are roles with respect to engineers, like specifically predicting battery remaining life, developing different sort of apps to monitor different sort of performances. And the best place for sort of upskilling students for these roles using MathWorks resource is to go step by step. So if students are very new, they can do some sort of online training. So we have some very basic courses with respect to modeling, circuit simulation, power electronics, battery on-ramp, where they learn the basics about these technologies. And then we have something known as a ready-to-use curriculum. Specifically with EV, we have something content that covers all different steps: modeling and simulation, motor control, power electronics, battery management, vehicle dynamics, uh, and what we talked about, like how to create system level vehicles, virtual simulation, all those aspects are covered. Okay. So we have the content here. If you are interested, just feel free to reach out to me. I will be able to share this entire content with you end to end. And lastly, hardware is also a major focus. So MathWorks supports a lot of hardware. Specifically for motor control, you might want to go with TIC 2000. So we have very good examples that can be implemented if you have the hardware at your end. Directly from the simulation environment, the algorithm can be ported to the hardware, and one should be able to test it out. Finally, there are some projects also. So students should actually take up very relevant projects. So MathWorks has a project page where students can take up projects. Yeah, and hopefully, I hope all of you found something useful in today's interaction. And let's hear from you if you have any questions, any doubts, or anything you'd like to hear from me, or any resources that you'd be interested in. Please let me know.
Thank you so much, sir, for sharing your valuable insights with us. We will now have a short Q&A session. I request participants to kindly interact directly with our speaker.
Good evening, sir.
Yeah, good evening, sir.
So basically, the AI can replace the smart BMs, right?
Sorry, I think there is
AI can
some sort
replace
of
smart BMs.
smart PMS.
Yes, yes. Can
I
AI
think there is
replace the
some
smart
background noise, so I cannot hear it clearly. Would it be okay to just post it in the chat? I will take a look at there. Yeah. Sorry, I couldn't hear that. So please do post it in the chat. I will try to take a look at that.
Good evening, sir.
Yes, sir.
Yeah, I am from Christ Engineering College. I would like to know that you had already mentioned about some courses that are being carried out online for students as well as those who are interested. So, what will be the duration for these courses? Is it possible for students to complete these courses during their beta course itself, or they have to join it after their beta courses?
So the courses that I was talking about, students can actually sort of take it up at their end in the BTech itself. So all of these courses that I was talking about is available in the place called MATLAB Academy. So all they need to do is just log in. So specifically Christ and Christ University, you have access to these courses. So you will see it here. The relevant courses which are there, it's all online. It's like there is an online version of MATLAB which is there, and the courses are self-paced. I mean, student can take their time to go through the courses. It will give them the steps step by step. So just to talk about system composer on ramp, so you can see from the ticks that somebody has completed that. It starts with at the very top, they can just get started with the course. Takes about 1 hour to complete, and everything runs on the browser itself. So they do not need to install MATLAB also. And once they finish, there is a certificate and progress report part where a certificate is actually going to get generated. So anybody who completes the course, like you see, in my case, it shows 17%. So they will get a certificate if they complete the entire course. And if you need to track the progress, they can share it with other users also. So they can share it with any other faculty or anybody who is giving them the course, they can share it with them also. And also courses are quite rigorous. They can go step by step from one part to the other.
Thank you, sir. Thank you very much.
Thank you. I think there is a question on like, can AI replace smart PMS? Okay. I think AI won't be something that is going to replace things right now, is what I can mention. But what people are trying to do is that people are trying to sort of bring an AI model also into the environment, into the systems, and then they're trying to compare with conventional what sort of accuracy you are getting and with AI what sort of accuracy you are getting. In some cases, there is a trade-off with some decrease in accuracy. If an algorithm is able to run fast and make predictions very fast, then that is something that people are actually looking at adopting. So right, not like a replacement right then and there of conventional working systems, but AI is sort of working in tandem and trying to see whether some tasks can be automated using AI and whether it runs fast with a certain acceptable level of accuracy or not. We saw it, we did see, right? It has some problems sort of tracking the discharge curve, right? So there are still challenges, but a lot of work is actually going to make them more accurate.
Good evening, sir. I'm having one question.
Sure, ma'am.
Yes, you have mentioned regarding the Kalman filter in your presentation. Could you please elaborate what is the major difference between the Kalman filter and the AI? This is my first question. And if we are going to use the hybrid approach for the Kalman filter and AI, so will it become the lightweight AI model?
That I cannot accurately say.
Okay.
That whether it will be lightweight. But what I will just show you a resource page. We actually have a blog that does it. So what basically Kalman filter does is that it actually has a mathematical model. In a way, it will have something like this. Like there is a mathematical circuit behind that. Specifically to model charge dynamics, it will have certain components. So what Kalman filter does is that it updates them in real time. So you take the equations that comes from this sort of circuits, okay, and then you can create certain equations which you sort of parameterize as states. So you will have the entire model. So it's a mathematical model which is there, and it has to be updated during in real time. So there is a mathematical process for updating that particular model. So we take sale voltage data, current data, it goes into that particular model, and then it makes the predictions. Okay.
Okay.
Okay. So because there is some sort of mathematical process, recurring process which is there, it takes a bit of memory. So memory-wise, it is not that efficient as an AI model. So that is why we actually replaced it with an AI model.
Okay, fine, sir. Thank you so much, sir.
Sure. Thank you, ma'am. That's a very
Yes.
good question.
Yes.
So if there is somebody interested, I'll just drop this link in the chat. It gives you a more detailed overview about measuring state of charge through different sort of approaches. Okay. Okay. So we are at 7:33. Probably I will stop sharing, and feel free to reach out to me if there is anything specifically. If you're working in this area of electrification, please feel free to reach out to me. And thanks a lot for joining me, and have a good time, all of you.
Thank you once again, sir, for patiently addressing the queries. I now invite a participant to kindly share a brief feedback on today's keynote session.
I think sir has some challenges like speaking. So if there are any other participant who would like to talk and give a brief summary, please feel free. And thanks to Mohammed, Jasim sir, I know you might have some challenges with the network at your end. Anybody else who would like to
Okay.
talk, please feel free.
Since there's no one, let's
Sure,
move
ma'am.
forward. So now, as a token of our appreciation, we take this moment for the virtual presentation of a memento and certificate to our esteemed speaker, Dr. Debanand Singh Deo. Thank you once again, sir.
Thank you, Freya Rose, ma'am, and thank you to the Christ University team. Yeah, thank you very much. Thank you very much.
Okay, thank you, sir, for joining. From the EEE Department of Price Engineering College, on behalf of the college, as well as the organizing team, I extend my sincere gratitude to your session. It was indeed a great session and informative session because some of the faculty members are doing research in this field. So it is very helpful for us. Thank you once again, sir,
Thank you
for
very
joining.
much, ma'am. Thank you very much,
Thank you.
ma'am. Yeah, thank you. Okay, then I will drop off now. Thank you.
So next, we are moving to the next session. Next session is handled by Dr. Malati ma'am. So Malati ma'am is already present here. Good afternoon, Malati ma'am. Good evening, Malati ma'am.
Hi, good evening, everyone.
So we are moving to the next session. Over to you.
Okay, just hold on. I would like to share my screen first.
Ma'am, 1 minute.
Welcoming. I invite Alex for the official welcome address.
So, once again, good evening, everyone. We will now proceed to session 2 of today's program. It's my honor to introduce today's distinguished guest, Engineer Dr. Malati, an accomplished researcher and academic leader in the field of photonics, fiber optics, and laser technology. Dr. Maladi holds a bachelor's degree in electrical engineering from the University Tun Hussein On, a master's degree in telecommunication from the University of Malaya, and a PhD in photonics from the University of Malaya. Currently, she serves as a professor in the Faculty of Data Science and Information Technology at INTI International University, Negeri Sembilan, Malaysia, where she actively contributes to teaching, research, and international collaborations. Her research spans artificial intelligence, photonics engineering, fiber optic sensors, and laser applications. She has made significant contributions in developing fiber optic sensors for monitoring humidity, temperature, and chemical concentration, as well as exploring nanostructure coatings to enhance sensing performance. Presently, her work extends to D-shaped fibers, microbottle resonators, and surface plasmon resonance techniques for advanced applications in food, gas, and environmental sensing. Dr. Maladi's expertise is reflected in her numerous publications in reputed journals such as IEEE Census Journal and her collaborations with local and international universities. Her dedication to innovation and sustainable technologies is also evident through her active involvement in community initiatives such as Innovative Sustainability Challenge, which empowers young minds in the field of green technologies. Beyond her research, she is deeply committed to education, mentoring, and inspiring the next generation of engineers and scientists. We are indeed fortunate to have her with us today to share her expertise on AI and IoT in EV monitoring and predictive maintenance. I now warmly welcome Dr. Malati to lead today's session. Welcome you, ma'am.
Thank you so much. So let me confirm with you all if you are able to view my screen.
Yes, ma'am. Yes,
Okay,
ma'am.
thank you very much. A very good evening, everyone. I would like to extend my gratitude to our distinguished attendees today, respected colleagues, industry leaders, and also fellow innovators. It is really a great privilege and honor to be here today to share my insight on the topic that stand at the crossroad of technology, sustainability, and also the human progress. So now, looking at the title Artificial Intelligence and the Sustainability through Internet of Things in Electric Vehicle Monitoring and Predictive Maintenance, I would like to touch a little bit on a pathway towards the Sustainable Development Goal. Today, we are not just discussing about technology, but actually we are discussing about the movement, a movement that seeks to redefine how we travel, how we consume energy, and ultimately how we care about our planets. So before I move on, let me introduce about myself. I'm Malati. I'm currently a professor at Inti International University. I've obtained my PhD from the University of Malaya in the area of photonics engineering. I'm a chartered engineer of IET and also a professional engineer by the Board of Engineering Malaysia and also a professional technologist from the Malaysian Board of Technologies. All right, now moving into the title today, let us begin with the bigger picture. The electric vehicle ecosystem. Okay, now we are looking at the evolution. All right, now the EV ecosystem is no longer in its infancy. It is actually through a decade ago, EV has been experimental, which suit a niche group of environmentally conscious drivers. But today, if you look at EV system, they have entered the mainstream with the support of government, companies, and also consumers, alike with embracing them into the future of mobility. This is what we see today. Yet, if you look at EV's ecosystem, right, it is not just about cars, but it includes the charging infrastructure, the lifespan of a battery, motors, software platform, and even the data-driven services. So the ecosystem now extend beyond the transportation, which influence the energy grids, urban planning, and even national policies on the carbon neutrality. So you can see that it is now the role of power electronic, AI, and IoT, which have increased the data-driven decision making it in mobility. This is what we are trying to look into the topic today. Why predictive maintenance? So now the first thing that we would like to look into is what are the challenges that we are facing in terms of traditional maintenance. What are the reactive and cost that is involved? What are the predictive proactive data driven? And what are the benefit that we can help in reducing the downtime and improve the safety of lower costs? Now, this rapid evolution bring opportunity, but it is also introduced a new complexity. And this is where intelligence monitoring and predictive maintenance come inside. Why do we need this predictive maintenance? It is because the traditional maintenance models were reactive, waiting for things to be break before fixing them. But with EVs, the stakes are higher, you can see. A failure is not just inconvenient, but it also compromises safety, increase the cost, and it slow down the adoption. Consider this, the EV battery represents up to 40% of vehicles' total cost. If it is failure, the entire economic equation of EV ownership will also collapse. So it is necessary to have a predictive maintenance which could powered by a real-time monitoring, and there is a necessary of AI-driven insight which can ensure that potential failures are detected earlier and it is able to address proactively and often can be prevented. In other words, predictive maintenance is not a luxury, but it is a necessary for ensuring that EV can remain reliable, efficient, and accessible. All right. What are the key challenges in EV maintenance? Number one, we look at the battery aging and what are the unpredictability, what are the complex electronics that are involved in this integration, what are the dependence on charging infrastructure, and finally, we have the cyber security data privacy concern. Let me elaborate a little bit about this. When we talk about battery degradation, we need to see how we monitor and manage to determine its performance. That's the first thing. When we look at the motor reliability, it is influenced by the torque and vibration, which is often difficult to measure without the presence of smart sensors. Data complexity is involving when we using the EV, it is able to generate terabytes of data per year. So making sense of data requires an advanced analytics and also AI. Finally, when we talk about cost, definitely the cost and adoption barrier is particularly emerging market where infrastructure may not yet be fully developed. You know, the reason behind this is that when we are dealing with large amount of data, cyber security and data privacy comes into concern. It is very important to address the cyber security and data privacy because we are dealing with a large amount or high volume of data. So this is where the future generation have to look into the issue. All right, now these challenges are precisely why we must learn to innovate things. Okay, now let's look at IoT data in action. When we incorporate IoT into the data, what happens is that we are able to monitor the followings. Number one, the temperature of the battery, the voltage, current, what are the motor vibration in presence, how do we monitor the tire pressure, braking system, and in fact, with IoTs in presence, we are also able to monitor the driver's behavior during the tracking. All right, now IoT embedded in EV tracks critical parameters. For example, the parameters that I have listed here, temperature, voltage, and current. So with this, imagine if you have an EV system as a living organism. So the IoT is working as a sensory nerve, capturing signal from every component that is embedded into the EV. So by just like this, looking at a human body, sensing alone is not enough. We need a brain to process. So that is where AI intelligence step in. Okay, so this is how it works. So at this point of time, a vehicle actually need to initiate communication so that the person who are controlling or monitoring the EV will be able to perform the action that is required. So you can see it is not just about battery controlling, but also by incorporating sensors, we have the communication between the vehicle and the sensor is able to detect any consequences that we are facing during the use of these EV cars. And when we are dealing with a large amount of data, that is where we need the presence of cloud. And cloud incorporation with AI will be able to actually give us a prediction and also to respond to the problem that we are facing at this particular point. So this is where IoT data in action is incorporated. So when we look at Internet of Things in EV, using IoT, we are able to have smart sensors and also telematic. And this will be able to connect with diagnostic system and your vehicle will be able to communicate with the cloud. Okay, so we will be having a vehicle to cloud monitoring, and if there is a presence of OEM, which is the original equipment manufacturers, OEM will be able to access the control on the machine remotely with the presence of network. So once again here, the ability of the vehicle to be connected to the network is very important. All right, this is what I tried to mention to you just now. So a vehicle can initiate vehicle to cloud communication by having the ability to sense the speed, the position, and also the communication is needed when there is a presence of cloud server. All right, so this is something that we must take note. Okay, now, what is the role of AI in maintenance? The role of AI in maintenance is that AI is acting as the brain of this entire ecosystem. Using machine learning model, AI can analyze historical patterns and also the real sensor stream to detect if there is a change. It will be able to predict when the battery will degrade, for example. Secondly, when the motor may overheat, or when the tire pressure irregulates, which can actually compromise safety. AI is just not about prediction of failure, but it can also provide recommendation for optimization. For example, it can suggest optimal changing or charging habits to extend the battery's life, or adapting braking strategies that can reduce wear and tear. So there is an importance of using techniques such as fuzzy logic neural network, KNN modelings, which are being fine-tuned for EV system. So some of these techniques focus on gradual human-like reasoning, while others can deliver highly adaptive data-driven solution that actually can help to overcome any under complex condition. Okay, before I continue, can you all hear me clearly? Can I get a confirmation?
Yes, ma'am.
Okay, I'm so sorry because I can only see my screen. That's the thing. All right, thank you. Let me continue. Okay, when there is a combination of AI and IoT framework for the electric vehicles, you can see that the presence of IoT sensors is able to monitor battery, motors, and tires. Okay, now when I talk about IoT sensors with all these sensing elements, we need a network that is able to communicate, because we are dealing with large amount of data. So the IoT gateway come into presence. So when we talk about IoT gateway, you have to take note that we need a strong network to reduce the latency. So for example, here I've given you a sample 5G. All right. Why do we need 5G? Because we need a broader band. At the same time, we want to reduce latency. Okay, now let's talk about V2X. Okay, what is the meaning of V2X? V2X means vehicle to everything. Okay, we need a communication between vehicle to another vehicle and also vehicle to the infrastructure. So this will enable the vehicle to interact with the surrounding, and this vehicle infrastructure is very important because it has to support the things that is present in the infrastructure. For example, even someone who are using the particular infrastructure, and it has to be supported with a strong network. Then we introduce cloud. What is the use of cloud? Is to store your data. Okay, and now we are looking at edge cloud. Why? Because we are trying to bring the data as close to the infrastructure that we are trying to troubleshoot or monitor, so that we can reduce the latency. So this is what we are trying to achieve when AI and IoT framework is designed for an electric vehicle. So with this, we will be able to support mobile, OEM, and also the services. All right. Okay, now let's move on. At the edge near the vehicle, IoT sensors are able to capture and process the data instantly. And at the cloud level, a massive data set are aggregated and analyzed, which will enable the fleet-wide insight. So So through AI model, predictions are generated, warning can be issued, and even automated adjustment can be made in real time. So this framework that you are able to visualize here will be able to operate not just like a vehicle, but as a smart connected entities. So it is part of a broader digital ecosystem. So now moving to edge computing in EVs, we are able to support real-time analytics on the vehicle. It is able to reduce latency versus only cloud solution and also enhance the security. Okay, so imagine having a virtual replica of your EV running parallel to the physical vehicle. Every vibration, every temperature fluctuation, and every charging can be mirrored in real time. So with age in EVs, it allows for a faster, more efficient, and more secure operation. And it also allows processing data closer to the vehicle rather than relying solely on a centralized cloud computing. Okay, so this is how edge computing can be better than the normal cloud only solution. All right, now talking about digital twin application, just now I mentioned if we are having a virtual replica of battery and motor system, what can this help? Okay, with replica, virtual replica battery and motor system, which are actually focusing on the temperature fluctuation, charging mirroring in real time. So with this, it allow manufacturers and also operator to test what if the scenarios occur. For example, what happens if the EV is driven in extreme heat? For example, number two, what happens if the battery is charged more frequently than average? Or it want to even test the behavior impact of motor health over the years. So using digital twin application, these questions can be addressed without risking the physical vehicle, unlocking the unprediction level of optimization and service. So this is a simulation of wear and tear, and it can help to continuously optimize using a real-time data. Okay, now talking about cyber security and data privacy, which I told you earlier, something that we need to focus, because at the moment, right, people are creating EV hoping that it could actually solve the current issues. Okay, rather than having, we are facing the depletion of fuel. Okay, so that is why we have migrated into EV. All right, and when we talk about EV, it comes together with EV IoT. Okay, why we need IoT? I've explained to you just now, because you want to monitor the vehicle. All right, okay, now why do you need AI? Because you want to predict when there is a situation that occur, how to overcome it. Okay, but we are lacking behind in terms of cyber security and data privacy. But with the great connectivity actually comes great responsibility. Okay, it's our responsible to address to this issue. Okay, EV are in many ways computers on wheels, correct? You agree with me, right? Okay, they are connected to network, they are connected to the cloud, and sometimes to the grid itself. This connectivity can actually raise the concern of cybersecurity and privacy. So how do we ensure that the sensitive driver data is protected? How do we safeguard against any attack that could compromise not only the single car, but the entire fleets? Okay, this is where collaboration is needed between engineers, cybersecurity expert, and even policymaker, and they have to come out with an essential policy. All right, without a strong trust in data protection, public adoption of AI IoT enable EV will become slower in the future. So this is something that you can actually look into for future research. Okay, so I'm just bringing to you the idea how we can extend our research to address the importance of the problem that we are going to face in the future. All right, because we need to protect the EV IoT network. We also need to ensure the data confidentiality, and Next thing, AI, okay, for anomaly detection in network is also need to be addressed. Okay, now this is some case study that I've brought for your information. In Tesla, okay, Tesla have set the benchmark with over-the-air updates, predictive battery management system, and real-time vehicle health monitoring have been addressed, okay, using Tesla. Using Nissan and BMW, it is able to monitor IoT-enabled telematic for EV health. It is also able to connect with the cloud-based predictive analytics, and it also have integration with mobile apps. So this is what Nissan and BMW have given us. On top of that, case study on fleet management is able to provide predictive AI to reduce the downtime. It also enable optimize and scheduling for the logistic. And finally, it provides data-driven operational efficiency. So these are no longer futuristic concept, but they are active and working examples that we are able to see. And there's a lot of studies that have proved the benefit of AI and IoT integration, where the benefit have profound on the reduce of maintenance costs, enhance the driver safety, extend the battery and vehicle lifespan, improve the customer's trust and adoption rate, and ultimately a progress towards our sustainable development goal, particularly in energy efficiency, climate action, and sustainable cities. So using based on the literature and whatever reviews that we are going through, we can see that the use of AI and sensor network to detect issues, which run internal diagnostic and apply software-based fixes like recalibration without driver's intervention, have been proven. Okay, so we can see all this on the literature. All right, now looking at the future trend in EV predictive maintenance, we are able to also visualize that AI powered is self-healing vehicle. Okay, that means there is no need for the user or driver's intervention. When there is a problem that is occurring in our EV, so AI is able to come out with the prediction and provide a recalibration. So this is actually very good, okay, if you look at this. So on top of that, the integration with smart grid and also vehicle to grid system is enabling the EV to store and return energy back to the grid. Okay, I would like to elaborate a little bit about this. When we talk about V2G, that means vehicle to grid. Okay, it is bi-directional. That means the vehicle is able to draw the power from the grid and return the energy back to the grid. So this is something very good. Okay. On top of that, using AI-driven EV to EV communication. All right. Using EV to EV communication, that means vehicles can share performance data with one another, optimizing the fleet behavior collectively. And of course, autonomous fleet maintenance, you are able to predict the analytics that ensure the self-driving EV remain in the peak condition. Okay, so this is something very important that we can look into. So I hope you are able to understand how does the EV system work when it is incorporated with IoT and also AI. Let me move on. Okay, looking at the roadmap. Okay, so allow me to briefly run through, okay, this thing. So when we talk about roadmap for industry adoption, number one, the incorporation of sensor and IoT is very important. Okay, when sensor is incorporated into your vehicle, so that means there is where you adopt the IoT integration. So using this, this next step is when you're dealing with large amount of data, we need to have our resource for storage. So this is where we have cloud and we have edge AI deployment. And step number 3, we have the predictive maintenance adoption. That means if there is a consequences that we are faced, it is able to recalibrate. And at the end, you can see fully automation and self-repair EV system. Okay, so this is how it keep on progressing. So when there is AI and EV joined together, that means your car, for example, right? You can actually charge your car whenever it needs. Okay, EV will definitely communicate with the charging station, and this is actually able to overcome any hassle free. Okay, that is what we can see here. So the expected outcome for the future is that it will be a backbone for the next generation EV reliability. It enables predictive, proactive, sustainable mobility. It is able to drive innovation, safety, and trust in the ecosystem. So this is generally what we can visualize from literature, and we can see what are the need. Okay, in one of our current research work that we have done, we were actually focusing on battery management. Okay, so this battery management with fuzzy tune low voltage chopper, and we incorporated with machine learning control drive for the for this electric vehicle. And the objective of this study was actually a pathway towards SDG as well. So allow me to briefly run through my research work. And we have developed this system, we call it a novel BMS, using fuzzy tune low voltage chopper, and this have been incorporated with machine learning control vehicles. Okay, now a little bit about the introduction. So EV, our objective was to ensure it has zero emission, it is able to reduce carbon footprint. At the same time, battery management system, BMS, is critical for EV safety and efficiency. With this, we can smooth the throttle operation, and reliable power conversion will remain as a challenge, because we understand that BMS is the brain of the battery, which is also the heart of the battery. And with this electronic component, we are able to control the system. The objective was to achieve a safe, efficient, and long-lasting. At the same time, it is also able to protect the battery in terms of overcharging, overheating, deep charging, or even short circuit. And it was very important for us that we maintain the communication between our battery management and the EV system that will coordinate the performance of EV. All right, let me move on. So when we were doing the study, we actually did some review, and the problems that we would like to highlight was the limitation in throttle response, and we want to look at the smooth EV operation. So we found that the traditional DC to DC converter was facing high switching losses, and there was a need for intelligent, efficient battery and also motor control. Okay, the objective of this study was to enhance energy efficiency using a low voltage chopper circuit, and we also apply the fuzzy logic and machine learning for control. And the final objective definitely was to support multiple sustainable development goal, SDG. Okay, so the related work was addressing on PV powered EV proposed for sustainable energy use. So when we talk about PV powered, at that time we were working on electric vehicle that can offer a promising path towards sustainable energy by using the combination of solar power and EV technology. So our objective was to reduce fossil fuel and also to lower the carbon emission. So looking at the DC to DC converter, essential for EV power regulation. Okay, so at that point of time, we were also working on BLDC motor control, which was used to explore with various methods. So allow me to just run through a few things here, which was important. We were working on our methodology was to focus on low voltage buck boost converter as a core power unit. Okay, let me explain a little bit about this. When we talk about low power DC conversion, right, it was based on application. Okay, in most modern power conversion, okay, we are working on three types of power converter. The first type is a buck converter, which was a step down input voltage, and boost converter is used to step up the input voltage. When you are using a low voltage buck boost converter, right, actually we are regulating the input voltage, where the output voltage can be higher or lower than the input voltage. Okay, that's how it works. Okay, now moving forward, our experiment setup was connected to a PV system to actually buck boost the converter, and we were using a driving. Let me go backward a bit. Okay, we were working on the all right, BLDC motor controller, right? So this BLDC motor controller was actually via the IoT sensors, and the data that was uploaded into the cloud was enabling a real-time monitoring system, which is able to visualize three things: the voltage, current, and also speed of the EV. So using the BLDC motor controller, it is actually a DC motor, but it's a brushless DC motor, which can electronically communicate with electric motor, and it rely on what we call as a Hall effect sensor. When we talk about Hall effect sensor, it is actually changing the effect of magnetic field into voltage output. So at the same time, okay, the involvement of fuzzy logic controller is able to also improve the switching efficiency, because as you are unable to understand, it relies on human defined parameters. And on top of that, we have KNN based machine learning to ensure the predictive adaptive control, which is actually discovering the pattern, or it is able to make decision based on the data input. So this is how we propose on the, what we call that, on the methodology. So on the mode 1, we were using boost operation using our diode in reverse. And for the mode 2, we were working on the buck operation. And for the mode 3, we tried to combine both, and we are able to alternate the switching to ensure that the current flow is stable. Okay, and in our experiment setup, we were using PV system that is connected to the low voltage converter, and we use the BLDC motor as a load to monitor through the IoT sensors. And finally, we have a cloud platform to record the voltage and current values in real time. Okay, in the simulation results, the converter output shows the voltage and current that is stabilized. And using the BLDC motor, we can also visualize the improved performance that have been integrated. And we have the results that we obtain showing that there is an efficiency in the gain. Okay, now for real-time monitoring, we were using IoT and cloud. So the real-time battery monitoring and data logging was recorded accordingly, and this enabled to predict the maintenance using AI and ML model. So it is able to visualize the speed, voltage, and current trend on the cloud dashboard. So I will also share with you all the paper that we have written on this research work that you can actually go through, and if there's any question, you can always come back to me. Okay, all right. Through this research work, we have addressed the following sustainable development goal. So the first one is SDG 7. We are able to address a clean and reliable energy system. SDG 9, innovation, that means the process that we have actually recorded here is innovated, and it shows an improvement for the infrastructure advancement. And on top of that, we have also addressed it to SDG 11 to support sustainable and also a smart urban transport. And finally, SDG 12 and 13 to address the responsible energy use and also to support the climate action. All right. So as a conclusion, using this, the research that we have done, BLDC motor efficiency have improved via fuzzy and ML hybrid control. And the use of IoT is able to work for the real-time monitoring and performance optimization. And this work was aligned with EV technology with the multiple sustainable development goals. So these are the things that we are able to actually address over there. So this SDG contribution is an essence of technology with the purpose of innovation that can directly serve the humanity. If you look into the current pattern, right, every researchers are working for the what we call that we are working for the to address the industry 4.0 requirement, right? When we talk about industry 4.0, that means we are working on technology, and our technology is enabling us to address for the automation. Okay, things are controlled, automated. Okay, so but we are actually lacking in terms of human values over there. But if your research work is aligned with the human value, that means we are looking forward for IR 5.0. Okay, so whatever research that we are doing at this moment, right, make sure that you incorporate sustainable development goal so that you will be able to achieve IR 5.0. So I repeat again, IR 4.0 is more towards technology value. So if we incorporate our research together with the sustainable development goal, we will be able to achieve IR 5.0. Okay, so to conclude, AI and IoT, come back to my researcher. So AI and IoT are not just improving EV monitoring and predictive maintenance, but actually we are trying to transform mobility into a smarter, make sure, safer and more sustainable ecosystem. So looking forward, the scope extend to industrial application, hybrid energy source, and also a smart city integration. So we are now moving from IoT to IoE, Internet of Everything, right? So that means we are moving into a very smart city integration. So the future of EV is not just electrified, but it has to be intelligent, connected, and also most important thing is sustainable. All right, so the future is that IoT-based advanced real-time monitoring with hybrid sources, integration of three-phase induction motor for EVs, potential to extend to industrial and smart city application. All right, so ladies and gentlemen, the road to sustainability is not just to run away from fossil fuel, but actually to create a more intelligent innovation and also to have a good collaboration. Okay, so now let's come back here. All right, okay, so let's work together. We can accelerate this journey, ensure the vehicle of tomorrow are not just efficient, but also a sustainable contributor to the cleaner and greener planet. So with that, I end my sharing. If there's any question, I'll be free to answer.
Thank you, ma'am, for sharing your valuable insights and expertise with us. And we now open the floor for questions. Participants, please interact directly with our speaker. So I think he has no questions and everything is clear. All right.
Can I add something here? All right. I believe, right, everyone here are researchers, correct? Okay, and each and every one of us are working on a research work. All right. Okay, so now I would like to tell something. I would like to share with you. Before you step into research, the first thing that you have to do is to do a preliminary study. Okay, so in these preliminary studies, right, we will be focusing on the existing system that is available. So when we look at the existing system, the things that come to us is that what are the current researchers working on? So when today, right, even before I stepped in, I heard to another speaker's sharing just now. He was, it was really wonderful. He was sharing about us what is happening in the industry. Okay, now industry is working very hard to promote EV. Okay, that's the idea. Now, we have to look into, as a researcher, okay, there are two options for us. Okay, the first thing is we follow the research pattern that is available. All right. So when we follow the research pattern that is available, that means we will be adopting things that is already existing. Okay. So when we adopt, we come out with ideas that we try to improvise, we try to make it better. Okay. That's our idea. But what I am trying to share with you all just now was that besides adding besides enhancing the existing system, you also need to look at the future that is going that we are going to face. For example, there was two things that I highlighted. Number one, cybersecurity. Okay, cybersecurity means, that means when we are bringing our EV, okay, into the infrastructure, that means your EV will be able to communicate with the entire city. Correct or not? That means you are not just creating IoT into EV, but actually you are bringing your EV to communicate with everything in the infrastructure. So we call this as IoE. Okay, now when your electric vehicle is able to communicate with another EV, okay, that means they can communicate with each other. All right. So AI is controlling the entire infrastructure. We look at it on the positive side at the moment, right? Where we see that using AI, we are able to predict what is the health condition of the car, and the car is able to calibrate, able to self recover. Okay, that is what we are seeing at the moment. But in a long term, what happens? Okay, so I would like to suggest here, besides following the current research that's ongoing, you also can work on the other side, on the cybersecurity part, where you need to protect your EV so that it doesn't create complexity. Okay, so this is something that might be new for you to explore. Okay, so try to explore on this, and you might come out with valuable research work which can be very novel. Okay, and this kind of idea, if it is being presented, I believe your research is going to go to the next level, which I call as IR 5.0. So please take your time to explore, because I believe that some of us might not know what is the idea behind IR 5.0. It is actually to bring human values into the technology. So that means even though the technology is being monitored, okay, human decision is important on top of that. Okay, so that would be the takeaway for y'all. Try to explore about this, and I hope when I see you in the future, you will be able to share with me what you have found. All right? Okay, back to you, MC. Thank you so much. Any question? I would be happy to take the question.
Participants directly interact with our speaker.
Anyone? Have y'all thought about this? Any of y'all? Have y'all thought about this? Have you worked about this? Maybe you can share your experience right here as well.
So, all right, since there are no responses at the moment, we shall now move on to the next part of the program. As a token of our appreciation, we take this moment for the virtual presentation of a memento certificate to our esteemed speaker, Dr. Malati. Once again, thank you, ma'am, for your valuable words and valuable key points. And so we are winding up. And once again, thank you, Dr. Malati, for your highly informative and thought-provoking session on AI and IoT monitoring and predictive maintenance. Your insights have truly added great to this faculty development program, and we are grateful for your guidance. Thank you, ma'am, and thank you all participants. Thank you.
Thank you again. Hope to see you all in another platform. Take care. Good night, everyone.
On behalf of our institution and organizing team, I would like to express our heartfelt gratitude to Malati ma'am for taking out your busy schedule to be with us today. Ma'am, we are truly thankful for your insightful session. Though we know that it's 10 to 11:30 p.m. There, you graciously accepted our request and delivering your lecture with such energy and passion. So we are sincerely apologize for the late scheduling, which is overlooked while planning. Thank you for thank you very much once again for your patience, kindness, and understanding. Ma'am.
Thank you so much, ma'am, for the invitation.
Thanks.
Good night. Bye.
Thank you, ma'am.
I S T U V W Y Z the my soul do I S yeah it is K N B Q R S T U V what is B P for P for P for P for
P for
book